So this is actually this is the last sort of presentation, the last PDF. We're going to take it slowly. I don't think we're going to get through the end of it. So there will be you will have some slides left, or I will really run on the finishing slides in order to just give you the concepts. We are going to do, as I said, we're going to do the exercise as we go. So at some point I'm going to tell you, okay, so now please connect to the server, to the Euclid server, and let's write these few lines and see if you can compile them. And from this moment on, I'm going to say that every 10 minutes or so. Okay, so this is our new thing, let's do it now. And I'm going to wait for a few minutes each time for you to do it. Don't feel too bad if you don't. I'm going to sort of stick with the average thing. It means some of you will not get everything at every given moment. But in our experience, it's a better way to get a grasp in the beginning, is doing these small steps and not hearing things for 2 hours and then getting something and struggling with it. So, what is CUDA? Compute Unified Device Architecture. First of all, it stands for Compute Unified Device Architecture, if it means anything to you. This is the first successful attempt to make GPU parallelism comfortably accessible. There were previous attempts to program general purpose GPU, GPGPU, general purpose GPU, not just for graphics. This is the first good attempt. You get good performance, you have a good grasp on the actual hardware, so you can write really efficient code for the specific hardware. It gives you still quite a comfortable way to program in parallel. It started with CUDA C, it's now a CUDA C++. As I said, it supports quite a rich range of templates and everything from C++. There are some extensions, so most of the syntax is going to be really familiar because it's a C++ syntax. There are some extensions, some keywords that you have to add, some magic variables that we already saw. And there are also quite a few APIs in order to do things that just don't exist in C++, like managing devices, allocation of device memory, and etc. This session is I really like this introduction. You're in the video.
You don't have this slide.
You don't have this? You're supposed to have it. No, this is... No, I was supposed to go forwards. I skipped the 6 ways to SuckSpy. And you are now in page 2.
Okay.
So we found ourselves. So I really like this sort of session. It really introduces CUDA in essence. And you're going to tell me in the end if you feel it's complicated or not. And I'm going to try and balance your view of it. Okay? So what will we do here? We will make a really simple hello world example. And we will write CUDA kernels. A function that runs inside a GPU is called a kernel. We're going to write them. We're going to launch them. We're going to check that we got the right solution. We're going to allocate and deallocate GPU memory. We're going to synchronize things and see that we got the right results. All this in the next sort of 2 hours. And we're going to do vector addition. So the only thing that you need to know is C or C++. For this session, you need no GPU experience, so no graphics experience. Another thing that people think that if you need a background in graphics in order to do general purpose GPU, not so. Nothing to do with graphics.
People even do not understand that this card doesn't have graphic output.
Yeah, exactly. Some GPUs that are used for general purpose don't have graphics output, or it's disabled by the driver. Yeah. So you don't need graphics experience to program GPUs. I made a special achievement of doing a thesis in graphics without knowing graphics, but that's another matter.
Even if you have like 650 or something, it's better to have another graphics card, because when you do a calculation, your computer freezes. Screen freezes.
Well, it depends what you do. You probably do something quite specific in order to do that. Usually my screen doesn't freeze, so.
Depends on how heavy your code is.
Yeah, it depends how. Yeah, it depends which card you have and what problem you have. Yeah. So we're going to see these concepts, heterogeneous computing, so not just SCPU or edge GPU, both. Blocks on the GPU, threads on the GPU, indexing, the magic variables, how they are done. A new concept, shared memory, doesn't exist on the CPU. Sync threads, synchronizations of threads running on the GPU, again, no equivalent on the CPU. Asynchronous operation, handling error, and managing devices if you have more than one device. Now we're going to do until here, we're going to do it rather slow, because this is the part that introduces the concept. And from here we're going to see how much time we have, and we're going to do it faster or slower depending. This is GPU specific and it's more advanced. Okay? So, hello world. Some terminology. When you work with a GPU, the terminology is device is the GPU. And the PC, the CPU, is called the host. So we have host and device. I'm going to use these terms from now on. Okay, host and device. The reason this is called device is not GPU is because there are potentially other devices. You could have an OpenCL device. You can have an FPGA accelerator. So these are all called in general, not just GPU devices. This is the coprocessor. As I said before, you always have a host. Every system has a host, not just the GPU. The host runs the code. So what you would do in heterogeneous computing, you would have all of your code, and you'd take some parts of it, you'd make them parallel running on the GPU, and you'd keep some of the parts still serial, and they would run on the host. The way that it goes is that the GPU is a completely different entity from the CPU. Now, you might have found online, or you will find online ways that make the GPU much more in binding with the CPU. For example, joint memory. So you don't have to copy between the memories, etc. It exists. Use it if you want. It's getting better and better. In CUDA 6, that will come out publicly soon, it's much better than before. It's still not as effective as doing everything by hand, obviously. But if you see something that says you can allocate the memory on the CPU and the GPU can access it, no problem, you can try to use it. It will not be as effective. Okay, it's doing things as I'm saying now. And the way that it really works is that these are two completely separate entities. The CPU has CPU memory and the processor. The GPU has processors and its own memory. And the GPU works on its own memory. So what you have to do if you want to do something on the GPU, first of all, you have to give the GPU the inputs. So you copy data from the CPU memory to the GPU memory, and you do it manually, which means you have to write a line of code in order to do it. After you've done that, obviously after this operation has completed, you load the GPU program and execute it. It actually, this is the function call. It's a line of code calling the GPU, telling it to do something on this data, on the data that we just copied. When this operation is finished, you can perform another operation on the GPU directly, just linking more and more operations on this data, or when you finish, you copy the results back. Again, you do it explicitly. There is a line of code doing it. So this is very important. First of all, this is the execution model. The code that does that, the code that says, okay, now copy the data. Now launch the kernel. Now copy the data back. This code, the administrative code, runs on the CPU. The kernel itself, the part doing the heavy computation, is launched from the CPU and runs on the GPU. Okay?
But how you operate from the CPU to take the result from the GPU?
You copy it. It's a copy command. It's like a mem copy. Okay?
So the CPU operates on the GPU?
No.
Copy both directions.
You can copy to the CPU to GPU and GPU to the CPU back.
The administrative work is done at the CPU.
Yes.
So when you want to take data from the GPU, it's actually sending a command.
Give me this data.
To the GPU.
Yes, give me this data.
Now, if you want to stream the data, you run the same kernel, but you stream a lot of data, much more than
You can do that.
the GPU's memory.
You can do that.
Do you need to reload the program again, or you can
No, this
load only once?
that's not a good way of saying it. It's as if there is a big thing loading it. Loading it is just calling the function. It just loads. It just runs. It doesn't really load. Okay? You just call a function.
No, but the order that you specified here is first copy the input and then load the program.
Yeah.
But what happens if the data doesn't end? I mean, you have a program, and now you want to stream the data.
Okay. This is a more advanced concept. You want to keep streaming data and running on it as it goes. You can do that, but it's probably out of the scope of this presentation. It's harder to do. We're going to get to touch topics that deal with it in the very end. Okay? But we're not going to be able to really answer your question in depth. Okay, so this is a hello world. Yeah, many people have seen this code. Standard C, it runs on the host, and the only difference between this hello world and usual C++ hello world is that we're not going to compile it with GCC, we're going to compile it with NVCC. So actually, this is where we start writing code. Please connect to your favorite Euclid server. I'm told you've done this before and you're familiar with it. You have to connect to the server, and I think it puts you in the head node, and then you have to connect to one of the child nodes, so E1, E01 to E06. You've done that before?
No.
You just connect to the main node? Yeah. Okay, so everyone connect to the main node. Are you using Mobile Xterm? Yeah. No, you don't need it. It's easy. It's easier. So first connect to the head node as you would normally. Once you are in, write SSH E06. I'm going to look for something to write it. Yeah. So when you're already in the Euclid server, SSH E0 IU6, you can use 5, 4, 3, 2, 1. And you need a passphrase. That's the passphrase that you used in the first place. Same one. And when it's done, you're going to get your login, and in the end it's going to say E06 or 05 or whatever that you used.
This is CPU.
Yeah, we're logging in. We're just logging in. No GPU yet.
I'd like to see when we change to GPU.
You hang in there.
Where we stay on this node?
No.
Yeah. Okay. Are we in? Yeah? So make, I guess, I don't know, check what's around. When I got in, there was nothing in there. So you can write, we're going to write code now. You can write it here, or you can make a directory and write it there. But we're going to write a single file of code now. Okay? So open your favorite editor. Usually it's VI. What other editors do you have?
We don't load any
You
module.
want that we write?
Oh, yeah, sorry. You have to load modules. Yeah, sorry.
You have to load module on a node?
Yeah, on the node. You have to load it.
Head node.
Not on the head node. It doesn't. CUDA is not installed on the head node. I was told so. Module load CUDA. Big surprise.
Little
Works on a headset, but it doesn't work on a computer. Common not fun.
Yeah.
Again? לא שמעתי? It's okay? You have to write model the correct way, okay. Yeah. It was a typo. So those of you who've managed to log into one of these and load the module, just do that so I know. Okay. So, as I said, please open your favorite text editor and just print this simple C++ program, and we're going to compile it with NVCC. What? That's a really good question. Yeah, I guess you would. Yeah, do that. Yeah, what we're doing now is we're starting in really baby steps. We're writing a program, and the thing we're doing now is just making sure all the basic things work. So write this, open the text editor, write this, include stdio in the beginning so we have the printf working, and we're going to compile it with NVCC instead of with GCC. How should we call it? Yeah, I call it test.c. Oh, okay. That's actually a really good question. Usually, you call CUDA files with the ending .cu, not .cpp. It would work anyways because we're calling NVCC, right? So it doesn't care. We're calling it manually, but usually you would call it something .cu. Use anything you want. I use test. Oh, hello. They use hello word. You do whatever.
Doesn't have the mantle in the system?
Did you load the module? It should have something. So don't be lazy and do that main, because we're going to put CUDA code there in a moment. So.
It even works.
So those of you who finished, just the first one, give me like a nudge. You finished, it works. Did you compile it this way with NVCC? Yeah. So you have on the right-hand side of the screen, you have the instructions how to compile and run it with NVCC. So NVCC, the name of your file .cu, and if you've written everything correctly, you have a file and you can run it. Yeah. Again, I can't hear you.
When I'm using hash include stdio.h, it's causing an error.
When you are
Including the file.
stdio, it's a crash?
Yeah.
Do you have that?
No, have to include.
Did you include it? Can someone have a look? How many of you are already done with that?
You forgot the hash.
Hash include, what's that?
Include or include?
I think the code.
Yeah, make a space, I don't know. It looks okay. Make a space like here. I don't know, maybe it needs a space. Otherwise, I don't know. You can try that with these otherwise. But I don't know, this should work. It should work the way you did it. Just wait. מה השקיעה שהוא נותן? You said that it works with your code. Can I see the way that you wrote it? Yeah, it's exactly the same. Int main void. It's exactly the same. .h.
Ah.
Yeah, that would do it.
I forgot to say. Yeah. Okay. Ah, okay.
Okay. So, how many are done? Okay. We have enough computers and everything. You might consider, if you do want, you can team up, do it in pairs or something, because it's going to get less trivial in a moment, just marginally less trivial. Is it okay if I continue?
In the instructions, the dollar is just wrong?
The dollar is nothing. You don't write the dollar.
Okay, so hello world, if this is the name
of the file.
And A out.
This is the next instruction. You write nvcc hello-world.cu, enter. Okay? And to run it, you write n.type. Many times you have to write ./a.out. Okay? Otherwise it doesn't run. So, do you have the hello world?
Oh.
I'm going to take another look.
I need to doubt.
I know, what are these?
I did it with single quotes, double quotes, without.
Okay.
Not working.
stdio.h int main void printf hello world.
Return 0. RETURN.
Yeah, what is the... Okay, run it now, then let's see what... Okay, you have some problem that it gives like a compiler problem. I think the best thing to do is you to team up with someone. Okay, so are we there? Congratulations, you have compiled your first program with the NVIDIA compiler, with the CUDA compiler. Okay, so next thing, you can type as I talk. If you're comfortable, if you understand what I'm talking about, you can already type as I talk. But for me, the best thing is I explain something, the concepts, and then we sort of do it together. Okay? So this is your first kernel. No, actually, this is not even your first. It's your first program. And what happens here is that before printing hello world, we call a kernel. This is a kernel call. It's called my kernel, and it has this weird syntax. And right now, no arguments. And this is calling this kernel here that runs on the device. This is a kernel. And what you see here is a function. It has a return type which is void. All kernels have a void return type. You cannot really do a return from the device. It's not so simple. You have to copy data over the PCI Express. No return values. Okay? The return values are somewhere in here. You put a pointer, and the kernel puts some things in the pointer, and then you copy it to the CPU. This is your return. And here, right now, it's void, but you can put anything you want in here. Integers, pointers, anything you want here. And we're going to fill it with code pretty soon. And this is new, global, right? So the global, well, yes. Yes. Time travel. We were here, right? Okay. No. Something. Okay. So the keyword global that was added, it means that this is a kernel. This is actually the addition that makes this specific function a kernel that runs on the device and not a function that runs on the CPU. Because we are putting now the GPU kernels and the CPU code in the same file. And the same compiler, NVCC, is going to compile both of them. So we need some keyword to distinguish between the kernel GPU code and the CPU code, and this is it, global. So many of the GPU special keywords have this underscore, underscore before them, and something, and then underscore, underscore under them. And this specific one means that this is a kernel. It runs on the device, so it runs on the GPU, but you call it from the host. The administration is done from the host. So you call it from the host, and it launches this function on the device. Yeah.
When you call it,
yeah.
copy the code to the device?
Sort of, yeah.
Not the data.
Yeah. You copy the code, not the data. And you don't need to talk about it, because it happens without you knowing, and very fast.
It's something like, in the old days, putting the interrupt to the interrupt register of the CPU.
Yeah.
Assembly analogy.
Yeah, sort of, yeah.
But currently we do hello world in the CPU. We just create an empty function on the device, run it on the device, it does nothing, we return to the host and do hello world.
Yeah.
This is what is problem.
Yeah, this is what... Okay, for a while now, we're going to deal only with ridiculous programs. Okay? And after it's not ridiculous anymore, it's extremely inefficient. And in an hour and a half, we're going to get to mildly reasonable code, and then we will end. And then we'll finish. Yeah.
You earlier mentioned the option of transferring a pointer.
Oh, yeah. We're going to get there. That's an excellent question. We're going to show it first.
The meaning of pointer, I mean, the GPU is probably not able to write directly to the CPU.
Yeah, we're going to see that. Okay? Okay, so...
Compilation is always done in the CPU, correct?
The compilation is done the way we did it now with NVCC.
No, nothing there.
Yeah. Okay, so NVCC separates the code that we're writing into two groups, functions that run on the CPU and functions that run on the GPU. It compiles each in its own place. In more complicated cases, obviously you can do projects with make files that compile some of the code with GCC and part of the code with NVCC, or if you're using Windows, you have a Visual Studio solution, and it's very easy. You tell it that it's a CUDA project with inbuilt customizations, and then automatically the Visual Studio does everything except the CU code, .cu files, which are done by the NVCC compiler. So it really happens without you having to know much about it. For this tutorial, we're only using one file, no make files. It's just easier. Okay? Okay.
What is transferred to GPU on the declaration state or on the function code?
Why don't I... Just a sec. I seem to have... Okay. I actually am not sure what is the answer, but I would say in function call. Usually you don't notice it. It's extremely fast.
I already compiled it. It runs slower than with regular hello world. So you notice it.
Yeah. Okay. Okay. So the other thing that is new in a syntax way is calling the kernel. And the way you call a kernel, there are no arguments here, but if there were any arguments here, they would be in the parentheses just as usual. So you just call a function with arguments. The only thing that is different is this thing, this strange thing here. And what you do here is you tell, you know, in the OpenACC we said that you give the parallel compiler hints about parallelism. So this is a bit similar. It's a bit of a hint, or actually it's not really a hint. You tell the compiler something about the way that the parallelism is built. We're going to go into that now. The parallelism in CUDA is built from two layers, a layer of threads and a layer of blocks. If you remember block ID, thread ID, the magic words that were on the board before. So this is it. Right here you're telling it to do an execution with one block and one thread. So we're still in the ridiculous realm. Okay? Okay, that's everything that is required to perform a function on the GPU. Please adjust your code to fit this wonderful example and see that it compiles and runs.
It takes 1.49 seconds to to create this functional device?
It does.
Yeah. 1.33. I just did time for two compilations.
Show me that.
זה עם הקרנל וזה בלי הקרנל.
I have nothing to say. No, but זה לא דבר שהוא, it's not a thing that happens. I don't know what's happening here on this node and everything, but usually you just call a function and returns immediately. Yeah.
Maybe other people are not.
It's not working again.
Connect to a different node.
Are you on the home node? No, you're in E06 node. What's the error that you get?
Doesn't anybody run on E02? Doesn't anybody run on E02? Will they compete with somebody?
Show me the code again, please. Global. Comment the calling to the kernel, see if it works. Comment my kernel, see if it works. Yeah, comment this line. Yeah, see if it works. No? Comment the kernel as well? Yeah, comment these both lines. No, yeah. Next line as well. Right, how did, תכתוב מודול לא avail השני, איך קוראים לזה? לא פה, בקומנד ליין. מודול ליסט אולי? So how many of you got it to work already? And the ones that didn't get it to work, do you get really strange compiler errors, or what's your situation? Really strange Okay, so the thing is this. I wanted it to be a local machine because GPU computing does lots of weird things remotely, but it was supposed to work because it's command line. Apparently it makes trouble, so I don't know, give it another 2 minutes, otherwise team up. We're not going to solve these problems now.
זה גלצל פעמיים הקף תחתון פה?
מה זה?
פעמיים הקף תחתון שצריך להיות?
פעמיים.
כן, בסדר. עשיתי את הלואוד מודוליסט. נעשה עכשיו?
לא, המודוליסט רק מראה לך מה נטען. Yeah.
Find out what nodes people are running on to see if some of the nodes work and some not, because I'm running on 4.
All right, and it works? Okay, so we're going to do an improvisation. It's a good idea. We're going to see on which node it works. So did anyone get it to work in node 1? No. 2? 3? Okay, so we have 2, 3, 4? 5? 6? Okay, so the ones where it's not working, which node are you in? 1. So 1, you're the only one at 1.
No, I am also in 1.
You're working? So okay. That was a really good idea, though.
You compete on the device.
No, if you, the problem is in compilation.
The meaning of the right one, you said it is thread. It is just thread number or how many threads?
But later.
Because we try 4 and it print only 1.
Yeah. Later.
You have no explanation why does it take so long?
No, I do not. But it's not typical. The only thing I can say, it's not typical. It's not something you see.
What is this error message expected equal? אומר לי שהוא מצפה לשווה.
Did you write this code? Exactly this code?
ה-Hello World עבד, שהוספתי את הגלובל, וכבר בגלובל הוא לא עובד.
Yeah. Okay, so when we were setting this up, we had a few problems. One of them was that some CUDA versions worked and some were not. Some worked and some didn't work. And you might have a different CUDA version loaded when you load the model for some reason.
Just load CUDA.
Yeah. It loads whatever, and I'm concerned that maybe it doesn't load the same whatever for everyone.
We can all do module list and see what...
Yeah, you can do module list and see. For me, it worked with CUDA 4.2. And, okay, so who has it not working yet? Not working? Can you do module list? Tell me what version of CUDA you're using.
5.2.
Okay, the problem is that you need 4.2. Yeah, you need to load code of 4.2. It works for you with 5.5? Okay, so first of all, let me tell you, these are not typical problems.
Generally works better than 4.
So okay, can I have everyone's attention for a sec? Can I have everyone's attention? First thing, guys. So first, we're not going to be able to solve this within these few hours. So I suggest everyone who has it not working. I think, wait, guys, please, this is important. Everyone who has this working will probably have whatever we do next working as well. Okay. So if you don't have this working yet, please team up with someone who does have it working. For the sake of these few hours, it's going to make it much simpler. Just know that generally this doesn't happen. This is a feature of the Euclid server and the remote connection. And the talks we had with the IT person there, yeah, so I don't know why it's like that. I was told that CUDA 4.2 works perfectly, whereas 5.5 doesn't. Apparently 5.5 does work sometimes, and 4.2 does not work sometimes. Yeah, okay, so. That's a really nice way to socialize, if you don't already know each other.
וגם את החבר. That's it, the underscores. There are 2 underscores, but I believe that most people have 1 underscore.
I've seen people who put 2 underscores and it didn't work.
2 underscores and the space in the void.
You know what the problem was?
No.
And the space in the void, before void.
There is a space.
There is a space.
That I use the file name with the...
Okay, I can't hear 2 people. I talk about parallel, but I don't do parallel. So I'm not a woman. I can't do 2 things. So you have a suggestion that people didn't put spaces. I did see code that has spaces and it didn't compile. So.
So the problem was that I used the file .c instead of file
.cu. Okay.
If you have the global inside, then
okay. So yeah, okay. I didn't know that it doesn't recognize it even if you manually put the NVCC. So apparently the file has to be .cu.
If it has a CUDA.
If it has a CUDA, yeah. So okay. Let me get a point now. Is everybody hooked up with a computer in which this compiles? Okay. So we are going to go on. What we did now is just a sanity check. It seems that it's a really good thing we did it, because if we continued, I wouldn't know if the problem is in the code or in the setting. Now we know that we fixed the setting problem, hopefully. But this does nothing, okay? So as the slide says, it's a bit anticlimactic. The next thing we're going to look at is vector addition. It's very similar to the SACSPY we saw before, it's only there is no scaling, vector addition. We are going to take a while to get there, though. Okay, we're going to first add a vector of length 1, just adding 2 integers, and then we're going to build up to a vector. So, this is a kernel that adds 2 integers. Take a look what it receives, okay? A and B are 2 input pointers, okay? C is an output pointer. We're going to write our results there. And the line of code that we put here is just the line of code you would put on the CPU. There are no magic indexes. All the magic stuff will come in a moment. And this does something really strange, right? What it does is it adds a single integer on the GPU. So as I said, we are still in the ridiculous realm. Okay? But take a look how it looks. Take a look how this thing looks. You still have... Guys, I understand now that there's going to be more talks because we're also writing code and everything, but please, mercy. So this is a function definition as you would, right? This is what you do on the CPU, and we have that global that we're a bit accustomed to here, and that's it. That's a kernel. That's just a sec. That's as complicated as it gets in the syntax area around the function definition. And the execution is actually very familiar as well. And this is a kernel that works. We're going to run it in a moment, and then we're going to make it a vector. Okay? Yeah, your question?
It's a very stupid question. Can you please explain what we call a kernel?
Yeah. Every function that runs on the GPU is a kernel. That's the name. That's the name. A function that runs on the GPU, and it is called from the host. So you call it this function from the host, but it runs on the GPU.
Can you call a function from GPU to run it?
Yeah, you can. You can call a function from within here, and then we don't call it a kernel. We call it a device function. You call it from the device. A kernel calls a device function. But this is called a kernel, and it has this global keyword here. That's a kernel.
And the reason for this naming is just because it's like a sandbox.
It sounds really cool. And it's shorter than saying device function. So, okay. Okay, so let's take a look. You're going to write this code in a sec, but let's take a look at what happens to the CPU code.
The GPU also had jumps and functions.
Yeah, but please let me progress a bit and then questions, okay? So we've put the pointers here. We're going to use them in a moment to run on vectors. The pointers point to host memory or device memory? Device memory. Okay, since this function is going to run on the GPU, the pointers need to be to GPU memory. Okay, so we're going to see how it's done in one moment. We talked about this. So again, device pointers point to device memory. Host pointers point to host memory. If you want to copy between them, you have to do it manually with a line of code that we're going to see in a second. The only acceptable way right now to transfer data from the host to the device and back is with these lines of code that do a copy. Okay? There are CUDA APIs to deal with memory. Instead of doing malloc as you would on the host, there is CUDA malloc. Instead of free, there is CUDA free. Instead of memcopy that copies from host to host, you have a CUDA memcopy that copies from host to device, or from device to host, or from device to device. And then you can also free and etc. etc. So this is our kernel, and this is now going to be our main. We have 3 integers defined. we have 3 pointers defined. We are allocating data on the device, CUDA malloc. Okay, this allocates data on the device. How much data we allocate right now? Size, which is just size of int, because we're working on 1 int for the moment. Okay? So this is defining data of on the host and allocating data on the device. And we are initializing our data, A and B here, 2 and 7, just to have some data and not garbage. And here we use CUDA memcopy. Okay? So what we're doing here is we're copying from A and, let's look at the first line. We're copying from A, which is a host variable, an integer on the host. We're copying to the device pointer that we just allocated. And this is a memcopy. And we're copying size bytes, which we inted to size of float. And we're telling CUDA that it's a copy from a host pointer to a device pointer. There are now nicer interfaces. There are interfaces that just copy and you don't need to tell them if it's a device or host. But this, for clarity's sake, you write it. Okay?
This function runs on the host.
This function, this code is host code. Okay? What happens when the host calls this function might be that the host gets in contact with the NVIDIA driver and tells the NVIDIA driver, please copy this. And the actual copy might be performed by a hardware component and not on the host, by a hardware component of the NVIDIA card. You don't know that. But this code is host code. So once we've copied the data, we can call the kernel. And we are still using this 1 and 1. We haven't talked about what it is exactly, but now we pass the arguments as you would to a normal function. So that's a normal function call. Once this is done, you have to copy the result back. So again, CUDA memcopy, destination first, so from the device to the host, so it means CUDA memcopy device to host this time, of 4 bytes, and you have the result back. And the only thing left to do is doing a cleanup, freeing the memory that we allocated. Okay?
Can the device copy back data by itself?
No. To the host. I'm saying no. There is small print, but no. Okay. So that's going to take a while because it's more code, but let's do that. You don't need these. You have it written, right? So you can actually do this. Write this as your kernel and then do the main. Or you can start doing parts of it and compiling and seeing if you get strange errors. And okay, in short, let's all get to the position that we have this code compiling.
Why there isn't a man page for CUDA malloc?
I have no idea.
I cannot do malloc false variables in one shot.
You want to
Do malloc false variables in one shot.
Well, you can allocate 3 integers, just change size, but do this because we're going to have each of them being a vector in a moment.
Why is a double pointer?
Here, because this is a return value. It's a pointer, but it's a return value of this function. So you pass it by pointer.
After void you have double pointer.
Yeah, because this is a pointer and this is address of pointer.
Yes.
So it's a pointer to pointer.
Okay.
If you want to return it into the second, for instance, into B, you want to return the result into B, then you don't, you can do it?
Yeah, you can do it. You
C, normal C. Like normal C.
like,
Normal C.
yeah, you can do it.
This way, in the declaration of the function, usually in C you declare pointer to the argument, but in the function body you operate by value.
Again?
In the normal C it would be written int star A, int star B, int star C, and C equal A plus B without a star.
No. That's not true. That's the syntax. If you pass pointers, then here you have to either use the star or use an index. Yeah, this is a pointer. You can't use it without some sort of indirection. Okay, so this is, I think, the last time that we actually run completely ridiculous code. We're going to actually run vectors the next time.
Can you bring back the...
You have it. You have everything.
Where are the headers for CUDA malloc and all of this?
You don't have it?
No, the header files for CUDA malloc that we call it.
It says that it doesn't find CUDA malloc? You try to compile it?
No, I want to see the template. I mean the prototype.
Look it up online.
I want to know the parameters.
Look it up online.
But how comes that the compilers does not include the file because it does it?
This is a server in Cyprus that I've dealt with first time 3 days ago. I don't know.
If those variables, the A, the B, and the C, are actually allocated on the device, why do you declare them here? Or shouldn't there be any different type of declaration of those variables?
Look, when we go back in session, you ask me again. When everybody is listening, ask me again. Okay, so whoever has it right, pick up your hand. You have it working? You have it working? Yeah.
Could you explain a bit about the double pointer? What is the mechanism behind why you have first you have pointer in Euro, but you don't allocate it at all. You have pointer in the CPU, the DA, the BDC, but you allocate it only on the device. This is the CUDA malloc. And then you have pointer from the CPU, and pointer in the...
Yeah, I'm going to talk about it. Yeah. I'm going to talk about it.
It prepares for arrays. It will be an array. Not for one number. This is the reason for double point.
Well, that's the syntax. We're going to talk about it in a minute. Okay, I'm actually going to talk about it when we actually do a vector. That's easier.
Even if it's scalar, we must do it this way.
Yeah, you have. When you do malloc, you have to do it. Yeah, when you do malloc, you have to do it this way. Yeah.
You would like to see the result. You make A equals B equals C. What is the individual actually? We add some variables. What was this? No, B is just device for the device. C now. CUDA. No, you have here before F print or something.
Yes, but we
No, you can do the same.
What happens if you forget?
Try it. What happens if you forget to clean up on the CPU?
Garbage reminding them.
No,
It remains until...
It remains until the program gets out of context, you know.
You have a garbage collector in CUDA?
Not so much. That's a low-level optimization language, no garbage collection.
Do you expect high-level person like scientists to write scientific code?
On the CPU as well, not everyone who can write C++ writes real-time code. It's a different layer of expertise, and that's also a layer of expertise. So who has it working? Okay, the ones who don't have it working, do you have compiler errors or? No, oh, you're doing YNet? I see some guilty faces. Okay. Is it okay if I continue? I wait a bit more.
And then undefined. So for what is integers?
In principle,
Here is the one the first one.
you can well put it here. This is it true or not? Because you release it from the device, yes, not from the CPU.
How do you check how many cards you have on the node?
How many cards?
How many devices?
You can check it from the code. We're going to see that in the end of this. Okay, I'm going to go on now. If you didn't have it now, you get a chance in the next. We're going to write code again in a few minutes. But you don't want to miss this one because we're going to go into parallel now. So moving into parallel, we are in the second stage now, and we're going to do blocks. Okay? As I said, CUDA has two layers of parallelism, one through threads and one through blocks. And now what we're going to do is we're first going to work through each of them separately, which is never done. This is only for tutorial. Okay? This is never really done. So if it looks strange, it is. Those numbers that were here actually meant that we're running one thread and one block. So actually no parallelism. And it makes sense because we only added one integer to another. So no parallelism, right? What we're going to do now is we're going to run n blocks in parallel. And each block is going to add a different integer. Okay?
What's the definition of block?
We're going to get there. So we're going to do a vector addition on the device. Now it's going to be a vector. Each parallel invocation of add we refer to now as a block. So each time we call this kernel, we refer to it as a block. And the collection of all the blocks is called a grid. So if we're going to now work on 1,000 elements, a vector of length 1,000, we are going to use 1,000 blocks. And the collection of 1,000 blocks is called a grid. So each invocation of the kernel needs to work on a different index, right? So we have, let's say we have 1,000 elements. Each invocation of the kernel has to work on a different index, a different I. And this index exists in the magic variable blockidx.x. This is a magic variable. And our code now, which is going to add a vector instead of just an integer, looks like this. So we still have the pointers, only now you are adding a pointer with an index. So it still adds two integers into the destination, but which integer which index of integer comes from the magic variable block idx.x. This kernel adds a vector. Okay? So notice this. This is something I didn't say before, something principle. The way kernels work is that usually they perform quite a simple operation on not so much data. And the reason that they can be done in parallel is because you want to do this simple operation not just for one element, but for many elements. And independently. They are not dependent. And this means that you can call the same code with a different magic variable, a different index. And if I have 1,000 elements and I call this line, and the magic variable has the value from 0 to 999 in each of the invocations, the work gets done. Is that true? Yeah? Okay. So this is the kernel we are going to run now, and it's going to take obviously some modifications on the host side as well. So this is the kernel. This is what block 0 is going to do. It's going to add the first two integers. Block 1 is going to add index 1. Block 2 is going to add index 2, etc., etc., etc.
You just assume that you have an infinite number of blocks?
I am assuming that I can control the number of blocks. If I have 1,000 elements in my vector, how many blocks do I need? 1,000.
But you may need 100.
Why? I have 1,000 elements.
When they finish, they will continue.
No. This way, the way I wrote it. If I have 1,000 elements, I need 1,000 blocks. Okay.
You don't know how many CPUs you have on the GPU?
I don't know nothing. We are doing a very simplistic example which doesn't make sense. It's going to make sense only after another coffee break. Okay?
What is the grid in the block?
The grid is the collection of blocks. The collection is the collection of all the blocks. Okay? I think it's going to be really confusing until we really get to the place where we use both blocks and threads and really perform a full vector addition, and then it's going to make more sense. So this is how the host side changes, the main. We are doing n integers now, and so the size of the vector is n times size of int. We are going to malloc on the device. It's the same line, yeah, it's the same line, only now the size here fits 512 integers, not just one. So we've allocated an array of inputs and outputs, okay, just by changing the size here. And we are now also doing malloc on the host side because we need a buffer, right? So we are doing a malloc of size, and they have random ints here. They are emitting, somehow they are doing an initialization of the buffer just so that you don't have garbage. I don't think this is part of CUDA. Try it. I don't think this is part of CUDA. So do a for loop and initialize your values somehow. Do a for loop and just put at each element of this array, put something. Let's say put the index or something, okay? And all we've done so far, yeah, on the host side is we malloc more data. Not just one integer, 512 integers. This is all we've done. And now we're going to memcopy more data. Size here has been fitted to copy all of them. Okay, so now it copies all 512 integers. And this is the main difference. We're not going to write 1 anymore. It's n1. So n is 512. We have 512 elements, so we need 512 blocks. Okay? So this is the grid is a grid of 512 blocks. It's just a name.
It can be a million.
It can be a million. Okay?
Just size of the vector. That is all.
That just
size of the vector.
Just the size of my data. Yeah. And again, CUDA memcopy, take it out. Okay. Let's do that. Let's do, yeah.
Once you are done with the explanations,
אני לא שומע. I can't hear you. Yeah. So have this code with the n blocks running, and we're going to talk about it, and then we're going to take a break before going into threads. Excuse me?
Identifier n is undefined.
לעשות איזה... נפלא, תראה את הכל, אין לי מושג, תראה את הכל. שגיאות נהדרות. מה עבד לך ומה לא עבד לך?
כלום לא עבד לי מאז פשוט כתבתי from scratch את כל ה... זה חיבור אינטים, כן? זה עוד לא המערך.
אין לך פה את עד, איפה עד?
באמת.
לא, אבל איפה המימוש שלו?
זה... לא יודע, איפה המימוש שלו?
שקף קודם. בוא נגיד ככה, תכניס את עד להערה ותראה שזה מתקמפל.
זה ברור, כן, כי זה הדבר היחיד שהוא
אסנה. לא, זה, כן, יש לי את זה לפעמים.
זה בא לפני המיין.
כן, זה בא לפני המיין, אחרת הוא לא יכיר אותו, כמו פונקציה רגילה.
והאינטואיציה הראשונית שלך עבדה.
כן.
תצליח לקבל את הערך חזרה. אני עושה A ועוד B, אני מוסיף את C ומקבל את
כשאתה עושה מהם קופי ל-C בסוף, אתה מקבל אפסים?
אני לא מערך.
באחד?
יש לי A שווה 2, B שווה 5, אני מעתיק את A ו-B, ואז אני מעתיק את C חזרה, אני עושה פה את ה-add, זה נראה ככה.
Device to host ולא host to device.
How to assign values to AD and AB by random?
Well, you can do that if it works wonderful. If not, make a for loop and in each one put the index of the loop or something. Do your own random.
Like the random should work.
Well, if you include the right thing, it works. Exactly. Just do a for loop and put something there.
You can do random in.
Well, I don't think it would work. You have to include something probably to have that working. Try it. If it works, tell everyone. כבוד.
יש לך שאלה לא חשובה ספציפית לנושא הזה כרגע?
אפשר לעשות, אבל עכשיו זה אינטראקטיבי כזה. אם זה חצי דקה זה סבבה, אם לא אז חכה להפסקה.
כן, אז הוא חצי דקה. כשאני נותן את הבלוקדים X או Y ו-Z וכאלה, האם זה משנה כאילו הם בכלל ביצועים? כאילו, קראתי באינטרנט וזה כאילו חלק אומרים כך, חלק אומרים ככה.
זה יכול לשנות לקרנלים מסוימים. כמו התשובה היא תלוי.
אוקיי, אז נשאר לך.
So who has it working already? Someone has it working? Okay. Do you check for the results? Did you do like a check that it's the same if you would do it on the host? Did you check that you got the right results?
I've printed the results.
Oh, you've printed them? Okay.
For the first and last element.
Okay. You did it the scientific way. Okay. Since you have the time, you can also do it for just compare it with the host edition.
אני לא זוכר, איך פונים לאיזשהו אלמנט?
סוגריים מרובעים. הקוד קיים פה, זה הקוד של הקרנל.
בפרינט F אני רוצה לעשות פרינט F של A. אחד.
פרינט F זה עם אחוז D, ובסוף אתה כותב A, סוגריים מרובעים 1.
זה D, זה
So you have the code in your slides.
But the error is here.
Do you have it okay? Trying to? What are the problems? Do you get compilation errors or you're writing? You're writing it yourself or you're copying from the slides? Really writing it? Ah, okay. You copy yourself from the slides?
Right now. We don't have the slides in digital.
Yeah, that's true.
Otherwise it would have been...
Too fast, too easy. You have it?
I try to feel it.
So you should know, we have to do it.
Okay, this random int, I don't know if it works. Did anyone have it working? Okay, so it doesn't work. Init it yourself somehow. Put something there. So how many of you have it done already?
Results are not right.
Are not right? You have the wrong results? Right, it compiles. Come on.
No, I get an 8 instead of a 6 No, it's right.
The GPU is never wrong.
סתם, כן, אבל אני מקבל זיבולים, אני לא מקבל תוצאות נקבל.
יש פה איזה בעיה.
מקמפל, אבל מבחינת המספרים אני
Just a sec. So those of you who got stuck with initializations, initializing A and B, you could just do that on the host code. We just need something there, right? We only need something. So this is a loop running from 0 to n, and at each iteration I put AI to being I and BI to being I plus 17 or something. Anything like that would do, right?
Infinite number of function calls is going to be this way one function.
Yes.
זה מעובר קומפילציה אבל נופל.
אפשר להעביר ככה יומיים.
צריך לעשות malloc על ה-A וה-B, חייבים?
Yeah, but you have to malloc it. Otherwise, where would the memory come from?
But I didn't malloc the C.
You have to malloc C. You have to malloc it on the host.
C also.
You have to do what's in the slides.
אני עשיתי את זה כמערך, סתם, בגודל.
Yeah, you could do that. Since the size is small, you could do that.
אבל תגיד, החזרה מהקרנל היא סינכרונית? קרנל חוזר רק אחרי שהכל מושלם?
In this way, yeah. No, the kernel call is not synchronous.
יכול להיות שאני מעתיק את הזיכרון?
לא, המם קופי בא אחרי הקרנל. זה אוטומטי.
המם קופי בא אחרי הקרנל, אבל יכול להיות שהקרנל לא גמר ואני...
לא, זה אוטומטי, זה אוטומטי.
מה מסנכרן?
יש פה משהו מאחורה שמסנכרן את זה.
מה, אחרי העד? העד
לא, הקופי הוא מסתנכרן. המם קופי מסנכרן. Okay, so I don't know, I'm going to talk a bit now. I'm going to make sort of a review and then I'll stay here. I'm going to take a break and I'm going to stay and see why so many of you seem to have problems. So just call me, I'll go between. And then we'll continue. Guys, please, everyone, we're going to go back for 2 slides and then in the break, those who don't have it working, I can come and help you. Okay? So take a look, please. So far, we still don't have a really running CUDA code, but so far we've seen that we have the concept of host and device. Most of the code actually is still running on the CPU, including the code that manages the device. The code that manages the device runs on the CPU. And a funny thing about it, someone asked, for example, allocating data on the device, the line that does it is on the host. And the host even has a pointer for it. It has a pointer to memory that is on the device. If you try to use this pointer on the host, you're going to get a segmentation fault or something. You can't do that. But the hosts, you hold it as a pointer in the host. You use the global keyword in order to signify that a certain function does not run on the host but on the device. This function must have a void return type. And then you can write C. Guys. What?
Oh, sorry.
Yes. So you use the global keyword to say that this is a kernel. It must have a void return type. It executes on the device. You call it from the host. This is the kernel. This is the essence of CUDA programming, writing kernels. Everything you want to pass, you pass as parameters. You can pass just integers or floats, basic types, and you can pass pointers. Those pointers are pointers that are allocated on the device. And since the device can also put something in these pointers and then you can copy it back to the host, this is how you get your return values. We saw some new APIs, CUDA malloc, CUDA memcopy, CUDA free. These are usually very simple. So far, these are really simple APIs that completely resemble host functions. Malloc, CUDA malloc, memcopy, CUDA memcopy, free, CUDA free. Okay, completely the same, only with CUDA prefix. And we saw that we can launch parallel copies of our kernels using multiple blocks. Okay, this is still not real code, but we do have a sense of parallelism now, right? Because launching 512 blocks at the same time we have a different block performing the operation on a different pixel. And if I have the hardware to run 500 blocks in parallel, then the whole operation takes just an instant. In an instant, 500 cores run 500 blocks and finish the whole vector addition. Okay? The only thing I want to go back to is this block idx.x. This is the one of the magic variables. And it exists as soon as the GPU arrives at this line. Some variable pre-exist, are already existing. There is a scheduler on the device, on the GPU, that transmits this code to the different cores, giving them different block IDs. And later there are more magic variables giving them a different magic variable. So each time a core runs this simple code, it already receives a different index, and that's why it runs on a different data element. That's okay? That's the trick. That's the trick. We're going to talk about threads later. We're going to see how to use both threads and blocks. And there is lots of other stuff to know about the GPU that is specific. But the parallelism model is this. You run a very simple operation on different data. And the reason you're running it on a different data is because these magic variables give you a different index each time this line is reached. Okay? Okay.